Welcome to Chem 1A. Ryan's birthday yesterday. I hope everybody said happy birthday in office hours. It's funny, it's her birthday, and we're having like the worst day ever setting everything up. But she, worked heroically to get that done. So say thank you and happy birthday if you run into her on the street, which I guess is not very likely in Zoom. I got a beeping in my, I'm going to put the other one in just because, stand by guys, I got a funny noise in my earpods, and I'm worried the battery's dying. We played some music at the beginning there. We might have to chop that bit off the video to start with because YouTube might tag us for using a copyrighted song. So we'll just see if they do. One of the reasons we played it is some audio if I can, because it's just beeping. Still have audio?
I believe so, yes.
Still have audio testing. Good. Can you catch this? We stopped here at absorption and emission, and this quantum mechanics that we're doing, it kind of reminds me of songs like Dexy's Midnight Runners. We heard them with that famous song, Come On Eileen. And when you hear that, you get excited, you want to sing along, you want to be a part of it, and you're pretty sure they're speaking English, but you still don't understand half the words. So I wonder if some of you guys feel like that when you come to Chem 1. I know that guy's speaking English, but I'm not sure I understand all the words. It's like almost like a language barrier. And there are some people watching from around the world watching this, so there's a bigger language barrier there. We don't have too much of a language barrier among our staff. Melissa's from Minnesota, so there's a little bit of a language barrier there. But I think you're getting accustomed to listening to her say, "Oh yeah, that's a good one, don't you know?" So let's get on with our discussion of absorption and emission, and we'll go back here just a bit because we went through this late. So we were talking about energy levels, and these are energy levels. They're just generic, some quantized state. Maybe it's a standing wave. Maybe it's a circular harmonic or something. But discrete energy levels is what we get, and those come from standing waves. And quantization, we remember, comes from a boundary, put boundaries on a wave-like system. It's really a simple concept. When you bound waves, you get discrete waves that fit within your boundaries, others that don't. So you only register the energies of those that fit. The energy differences are what you can detect. So you sometimes you can calculate the exact energies of the states, and we'll do that. But the differences in energies are how you detect that quantization, because light coming in, we know now, comes in packets of energy, in photons. And if those packets of energy match one of the energy differences, then those are absorbed. So I just sent ultraviolet. That didn't match, the energy of that didn't match any of these. So it's transmitted, was not absorbed. If I bring in here lower energy photon, this one in the blue region, I'm saying that one does match an energy gap. And so it's absorbed. And when it's absorbed, it's removed from your spectrum. So you're bathing white light, say, on this, and you've separated your white light with a grating or a prism so you can see all the colors of the white light. You would notice that a very specific frequency, a discrete frequency, one frequency is absorbed by this system. And here's a green lower energy photon. That one also corresponds to the transition. This one was 1 to 4. The green corresponds to the 1 to 3 transmission. And I'm saying 1 to 3 because I'm saying these are quantum states, and I'm going to number them 1, 2, 3, 4. We always start with quantum level 1. We don't start with start our counting at 0. We start with n equal 1, and you guys already know why, because those numbers represent multiples of wavelengths. And you don't want to multiply 0 by your wavelength. That's 0 lambda. So you have to start at 1 half wavelength, then 2 half wavelengths, then 3 half wavelengths. So that's a 1 to 3 transition, and it would be removed from the spectrum, and so on. There was a yellow shot through there. That wasn't a energy spacing that we had, so that was transmitted. So you can already tell this substance, oh, I should leave this as a chem quiz. What color would this substance appear to be? There's a hint that a yellow photon just flew through there, and that yellow photon was bound for something, your eyeball. So you're going to see yellow. We also had ultraviolet fly through there, but your eyes don't detect ultraviolet. So yellow photons getting through. Oh, there it goes again. Here's a reddish photon coming through, and that one has appropriate energy for the 1 to 2 transition, and that one is absorbed by the system as well. So there's absorption spectrum, and the reverse can happen. As we know, you can have emission spectra. So now we have emission from this compound, and emission gives you emission lines. So now you have discrete lines. So now you're not broadcasting any light. You're not giving the system energy. You're just looking at the system once it's in an excited state. These are excited states because they're raised to a higher energy level. We also were playing Dexy's Midnight Runners this morning, so everybody was in excited state, but these are electronic excited states. If this is an electron, it could just be a wave excited state. Well, higher energy states are more excited states, and this process where you have an emission is often called, the process is called relaxation. I go from a high energy state to a low energy state. I relax, and that transition, those are also going to come at discrete frequencies. So there's the red and the green, and the blue photon can be emitted. And your emission spectrum will look like discrete lines. So that's the basics of spectroscopy. Spectroscopy is a general technique for investigating the structure of atoms and molecules. And we can't see atoms and molecules just through a regular microscope. And you know, the atomic force microscopy that I showed you, where you could detect the atoms, we're still not looking through those. It's still not an optical microscope. We are just measuring very minute changes in electrical conductance that's saying, oh, you bumped into an atom. And then we plot that after the fact. And the plot of that conductance shows where the atoms are. And it always annoys me. We talk about in this class, and we'll do it some more, popular culture, especially on TV and in the movies. Whenever you have a scientist portrayed in popular culture, what do they have? A lab coat, white lab coat. On their bench, there's always a microscope, because that's sciencey, and there'll be some beakers and colored chemicals. And it's hilarious. You literally see this on some television shows. They look in the and they say they can see the DNA. Oh, I can see the DNA sequence. It's like a crime drama or something. They go to the crime lab. Oh yeah, I can see that DNA. Or molecules. An optical microscope actually can resolve entire chromosomes. Chromosomes are ginormous, but nobody leaves a whole chromosome at a crime scene. You have to break down. That's a lie. They do leave the chromosomes, but chromosomes are generic almost. You have to break down to sequences of DNA to identify the person. So you go down to pieces of DNA that are below optical resolution, and you can't just look at them and see what they are. So you have to use these indirect techniques. Molecules. You shine light on them, and the light they absorb tell you something about their structure. In this case, if this were a molecule, electronic structure. And that electronic structure has to do with how the atom is arranged in space. And if it's a molecule, how the molecules are hooked together. So you can get structural information from this. And that's where we get structural information. You have seen people draw a water molecule, and we know it's oxygen and hydrogens. We know that because of spectroscopy, because anyone can see it in a microscope. So what does this lead to? Let's do a chem quiz related to this. So here is an energy level diagram. Quantum levels 1, 2, and 3. Energy increasing on the board, as we always do. So the emission spectrum is here. So this is the emission spectrum from that sequence, that arrangement of energy levels. The question I have for you is, which line, A, B, or C, corresponds to the transition, the emission, high level to low level, 3 to 1? So Ryan will start a poll on that. Think about it. Take a vote. I'm getting the beeping here too. Am I muted? Okay, and you don't hear any beeping on the audio. So this is just chirping in my ear. It's annoying. So go ahead, bring my audio back, and are you ready to show the poll results? All right, and I'm back on audio. Okay, guys, we've had a minute to think about that. I'll give control of the screen for a minute. That's always dangerous, but 160 of you already. So let's see what you're thinking on that. Equally distributed between 1 A and C on this. So let's talk about that for a minute in our small groups and see if we can come to one conclusion. I did not, can I be muted again? I did not set up Zoom here in advance. Hmm? Am I live? Okay, after the second vote, is this me or you? Let's see what you're thinking. The results of the poll are, everybody kind of has shifted to A from C, or a lot of us. So you're thinking A is the correct answer. And I'll tell you, I agree with the A's. I'll take back control from Ryan. And let me give you my thinking on this. We have emission lines, and we have this 3-level system. So we'll get emission lines from this. There'll be a low energy one. I can go from 3 to 2. That's relatively low energy. I can go from 2 to 1. That's high energy. Now, energy goes just with frequency. It's E equals H nu. So this is a low frequency photon. That's a higher frequency photon. And then 3 to 1, an even higher frequency photon. So C, lower frequency, B, higher, A, the highest. And you can see I plotted frequency going this way. So the highest frequency is the highest energy, and that's the transition I was thinking about. So I agree with you. A is the way to go here. Okay, let's take it up a notch. To which energy level scheme does this emission spectrum correspond? So we're kind of flipping it, flipped classroom. This I'm giving you is the emission spectrum. This are possible energy level diagrams. And this is real spectroscopy, because get this in the laboratory and you're trying to figure out this. So let's start the poll on that and see what you think. Melissa, I'm just going to join the room in advance so I don't have to go through all that rigmarole. So can you assign me a room? Is my audio on? Okay, let's see how you've been thinking for a little minute and a half here. About 100 of you have voted. Let's see what you're thinking. A lot of you, wow, 71% of you or more think A. So it's rare we have that strong a consensus to start with. Let's talk about it in our groups and see if you come up with a solution for that one that stays A, or somebody convinces you it's B or C. I think I'll just, oh, you've sent it to him, right, Ryan? So you can just switch to the next, or go back one and they can see it. Okay. Am I muted? Hey guys. Hey guys. Hello. Let's see. I have James. I have